Hello everyone. My name is Kamyar and I am a PhD student and doctoral candidate in the Heat4Energy project. My research takes place in the Laboratory for Refrigeration and District Energy, which is located in the Department of Mechanical Engineering at the University of Ljubljana. Let me explain why I am here. Did you know that 72% of the global primary energy consumption is lost after conversion? In more details, 63% of the considered waste heat arises from temperatures below 100 degrees Celsius, in which electricity generation has the largest share, followed by transportation and industry. This low-grade waste heat is often expelled into the environment through exhaust gases, cooling water, and other waste streams, contributing to energy inefficiencies and thermal pollution. Recovering and utilizing this low-grade heat offers substantial opportunities to improve energy efficiency, reduce operating costs, and mitigate environmental impacts, as the temperatures between 57 to 117 degrees Celsius account for 3,500 petajoule per year only within European Union alone. The organic Rankine cycle is effective for recovering waste heat above 80 degrees Celsius, but for lower temperatures, thermoelectric modules are the main solutions for now. However, they require a large temperature difference and have low efficiency below 200 degrees Celsius, which limits their use for low-grade waste heat recovery. In contrast to these technologies, the thermomagnetic generators are considered a promising technology, as the second law efficiency can be theoretically higher than any market-available technology. There can be no moving parts, and scaling down is not yet possible for vapor compression systems, which have the highest efficiency to date. This technology is based on the singular magnetic property of some ferromagnetic materials, which will undergo phase transition between the ferromagnetic and paramagnetic state near the Curie temperature, and such ferromagnetic materials are also called magnetocaloric or thermomagnetic materials. The thermomagnetic material changes its magnetization as a function of temperature, so they can be considered as a sort of thermal switch. The magnetic circuit in such devices additionally contains one or more permanent magnets as the source of the magnetic flux and soft magnetic yokes to guide this flux. At temperatures below the Curie temperature, the thermomagnetic material is in the ferromagnetic state and thus guides the flux. When the thermomagnetic material becomes hot, it changes to paramagnetic state and the flux switch opens. To generate electrical energy, an induction coil is required, which is usually wound around the flux switch material. Following Faraday's law, this flux change with time through a coil induces an electric voltage. The project aims to develop a 100-watt thermomagnetic generator operating between 40 and 80 degrees Celsius with over 10% exergy efficiency. It features a high-frequency regenerator that reduces viscous losses, enhancing performance. A demonstration device will validate the concept under various conditions. I will undertake 3 secondments to acquire the necessary knowledge for the successful development of the device. My first secondment will be at the Federal Institute for Materials Research and Testing in Germany. My second secondment will be at Magnorik, a pioneer of the field. Finally, my third secondment will be at Helmholtz Zentrum Dresden-Rossendorf, HCDR. Thank you for your attention.